Welcome to module 38 of object oriented analysis and design. From the last two modules, we have been discussing about state machine diagrams. These are UML behavioral diagrams, which are very important in defining and capturing the discrete behavior of a system in terms of a set of finite states, and a state here is at a higher level of abstraction than the state as we refer to them in terms of a finite state machine or a regular automata. Here the states are often called behavioral in the sense that the states may have certain entry activity, certain exit activity and internal activities and transitions. And we have seen that there are a variety of behavioral states, starting from the simple state to composite state and submachine state, and composite states in turn could be orthogonal or non-orthogonal, that is, they could be just sequential having one region, or they could have multiple regions. And we have also seen that the state machine diagrams so described need variety of other kinds of nodes for its complete description, and these kind of nodes are known as the pseudo state nodes, which include initial, final kind of node, and in addition it has for join this kind of node as well, which or choice nodes which define different kinds of control transitions in the whole state machine process. So, we will continue on that. This will be the last in the series of discussions on the state machine diagram. So, we will talk about the protocol state machine, and at the end we will briefly take a look into the leaf management system, the example we have been discussing often, and try to discover the state machine in that. So, this is just to recap that this is one of the behavioral state diagrams of an ATM that we have done, and I am sure you have understood this well, and if you not, please go through that again. Now, first about protocol state machine. Protocol state machines are a specialization of the behavioral state machine, and they are used to express the usage protocol or life cycle of a class. So, let us understand what was a behavioral state machine. Behavioral state machine, if we just take in the very simple form, I have a state S 1 and I have another state S 2. These are behavioral in nature. So, what did we have? For this I have an entry, for this I also have an exit, the same here, and I have some internal activity. So, they are behavioral states are kind of at a higher level of abstraction, defining, not only defining the overall conditions in which the system exists, but in terms of our modeling, the system at a micro level may be going through several changes because of the do activities that is happening in that state, but overall we see that the system is in a single state. So, we have seen several examples of that, but herein we, in terms of the protocol state, we are primarily interested to express the usage protocol in terms of the life cycle of a class. That is, in protocol state machine, we will not have the entry, exit or do activity of a state. A state is more a designator of what is the condition on the life cycle of an object of a class that the whole process is currently in. So, and we will see that actually when we talk about a variety of different state machine diagrams, quite a significant part of the state machine is actually protocol state machine, which just talks about the life cycle transitions without having further activity details amongst them. When we represent a protocol state machine, we usually engage a keyword protocol written in the curly braces, which designate that this is a protocol state machine. So, this is like before, these symbols are same. This is the initial pseudo state, this is a final pseudo state, final state, and these are the protocol states. So, once you say that these are protocol states, what you mean is these will not have entry, exit or activities within them. It just designates that this has happened. So, I could actually model starting with a protocol state diagram, and then when we get more information, we could elevate some of these protocol states to actually behavioral state by adding all those behavior. But the first that we need to identify is the distinct configurations into which a system should exist so far as our modeling is concerned. So, we are saying in terms of URL connection, there is a created, that is you are just beginning the process, and then if the connect event happens, you have been able to connect to that URL and you open, you are in open state, you are checking that URL, and when you close the browser, you have a close event which you takes to the final state. So, protocol states represent an external view of the class that is exposed to its clients, that is whatever the client is doing with that class, you will be able to see that in terms of the protocol state. The states of a protocol state machine do not have this, we have already mentioned. So, a simple, so this is a protocol state, simple protocol state running. So, protocol states will only have their names to represent. So, in terms of that, the protocol states also can have submachine states or composite states and concurrent regions. The concurrent regions make it possible to express protocols where an instance can have several active states simultaneously. So, the difference with the specialization with respect to the behavioral state diagram is in the fact that protocol states are just placeholder of configuration, but they do not have a behavior of their own. But otherwise, you can have a composite state, as for example, is being shown here, is this is a composite state runnable, and within that you have two protocol states, substates ready and running. So, this is part of, as you can understand, this is part of the process state transition diagram that we typically draw as a finite state machine. Here we are drawing it as a state machine UML. So, we say that these are the substates ready and running, sub protocol states, and so starting from the initial, you could be in ready, and if a from the ready, if a particular thread is picked up by the scheduler to run, you get the run event and your state changes to running. And then when that thread is suspended, because you have possibly run out of your time slot, then this is suspended and you get back to the state ready from the state running, or the process might yield because a higher priority process has come in. So, the process will yield and come back here. So, you can see that like in we have seen in terms of the behavioral state machine, here too we have composite states and here too we have the substates and so on. Similarly, we can have submachine states and we can have concurrent regions where the protocols run in parallel in concurrent, so that you have multiple states being assumed at multiple different points in the dynamic system. This is just another example showing you a keyboard operation. So, this is the initial transition, these are the different protocol states, and so by default, so these are the states as you can see, and by default you are in the lowercase character mode. So, if you press any key, then you send the lowercase scan code, because you want, you know that you are going to find out a lowercase character from the keyboard, and you continue back in the same state machine. But the moment you press the caps lock key, you have got the caps lock event, then you make a transition to the caps lock state, which is a substate of the whole composite state of keyboard operation, and wherein if you press any key, then you have the uppercase scan mode switched on, and each one of them will have the list of actions. This is the key press is the trigger that is happening for a state transition to take place. And in this state, if you have caps lock pressed again, then you will again come back to default. You will basically keep on toggling between these, and these are the different transitions that you can see. So, this is a typical way of representing or sample showing how the protocol state machine will actually look like or operate. In this context, I would like to also remind you about an example that we had talked about in quite a few modules earlier. Talked about an elevator, where we said that the elevator can work between two floors, and we tried to model that elevator in terms of certain static properties, which describe the elevator instance, but more importantly we looked at the dynamic properties of when it moves between one floor to the other. So, we said that the floor could have three possible values, so 1 and 2, the first floor and second floor, and x, which is indeterminate floor or the moving state. And we said there is a is moving condition, which defines whether the elevator is still or it is moving up or it is moving down, and the door is represented to be open or closed through a boolean. And so, based on this we could work out a state machine diagram for this whole scenario. And if you now, with all your knowledge of the state machine diagram, look back into this simple state transition that we had done, then you will realize that this is nothing other than basically a protocol state machine, because you have here all these different descriptions, the triplets defining what is unique about that state, and these events of trying to go up, trying to come down, or trying to open the door and so on, define the different transitions. Naturally, we can also think about this. So, this could be the first model of an elevator in terms of the state machine diagram, which is a protocol state machine, but we could also make this subsequently into a behavioral diagram, saying that, well, if it is say if it is one still open means it is on the floor 1, it is not moving, it is still, and the door is open. So, at this what will be the entry exit for this? The entry exit, if you see, the entry for this is open, right. So, somebody has pressed the open key, open button on the elevator, and only then you will enter this. And on exit, what you will have? You will have close. You may have close and up, but you will at least have close, because if you take this, you will have close, you will have, if you go this. So, you can see that the close is common between these both of these transitions. So, you can say exit is close. And what is the do action that this state might have is scan keys. So, these are different possibilities that will exist in that state, and having identified that, after we have a protocol state diagram, which is just looking into the different 6 different configurations in which the elevator can be, we could then endow it with all these entry, exit and activities, and try to bring out the real behavioral state machine out of this. For example, in another, if you take, say, if you consider this state is x, that means the floor is indeterminate, because the moving is up, that is, it is moving up and the door is closed. So, which means that certainly the entry is clear, entry is up, exit is clear, what will happen in exit, it will stop, and what actions are being taken, this is moving, right. So, this is going up. So, this activity is continues to happen in this state, and whatever else need to happen because of that, the motor has to run, the pulley has to turn in certain direction and so on. So, all these if you describe along with the state description here, then you will elevate this protocol state machine into a behavioral state machine. So, that is why we started by saying that protocol state machines are just specializations of the behavioral state machine, which give you a compact information in terms of the life cycle of the objects of the class. So, you can really see what these different life cycles are happening, and they will keep on continue to move around in between this protocol states, and will give you information in terms of how the system goes. Protocol states do have naturally have transitions, and often the transitions are guarded. So, a protocol transition is again a specialization of the behavioral transition and used for the protocol state machine, and has the following feature. It is a precondition or trigger and a post condition. Precondition, trigger and the post condition. So, precondition is what must satisfy before this transition can take place. Trigger is what makes the transition happen, and post condition is what must be satisfied once the transition has taken place. So, this concept we have been saying repeatedly in different parts of UML. You have seen these similar concepts in activity diagram. You have seen this concept in the behavioral transition as well. So, here if we see if it is if we are moving from a new to active state, then the precondition is it verified that this is a valid ID. If it is, then your trigger is activate that ID, and certainly the post condition is what will result from this is a unique ID. So, these are the typical ways you will write protocol transitions, and so this is the syntax for the protocol transition that you can get satisfied yourself. Certainly, in terms of the protocol transition, the precondition and the post conditions are usually constraints, that is that basically they are Boolean conditions which are true or false, telling you whether the precondition is satisfied or the precondition is not satisfied, or whether the post condition is satisfied or it fails. So, you could look at a protocol state machine diagram for online shopping, and here I have picked up an example where you can see really the different kinds of protocol transitions happening here. So, let us look at 1-2 of this. This is a unique you start here. So, this is the initial pseudo state, and then you have the new substate of protocol substate. So, the precondition is unique ID, because and then you create that naturally only if it is a unique ID, then it can be created. And then from this state you make a transition to the suspend state. What is the precondition? Is account dormant. So, if the account has been dormant, has not been operated for a certain period of time, then you issue a trigger suspend and put it to, that makes the system go into a suspend state. Similarly, in the new ID, if it is verified, we have just seen that, then you trigger an action activate and you get the unique ID and you reach the active state of the system. In the active state of the system, again you could explicitly ask to suspend your account. If you do that, you reach the suspend. If the password alert, for example, if you have keyed in the wrong password for a number of times, then it could lock and you get into a suspend state. So, all these you are expressing, all those semantics you can express in terms of the protocol transitions using the precondition constraint and the post condition constraint as applicable. For example, here you can see that you have a transition from suspend to active, which is based on the precondition that is lock expired. For example, when the password is locked, typically it will not be locked eternally, it will be locked for couple of hours, for a day or so, and beyond the expiry of that, this condition gets satisfied and then you get a trigger to unlock. So, you come back to the active state. So, in this way you could follow this whole diagram very carefully to see different situations and how they are modeled in terms of the protocol state transition using the precondition, postcondition and trigger models, and learn more about how this state diagram modeling happens. This is the same example where this is a little bit of annotation done, so that you have ease in preparing for understanding of what these different icons are. This is, as you know, the protocol state. This we have seen several times. This we have just explained the protocol transition. This is another protocol state, and this is a protocol state with a difference. This is a protocol state with an invariant. It says the account is closed, has no balance due. So, if that is the case, only in that it will get closed. So, this is the invariant which is important for this state. So, we will before we end, we will take a quick look into the state machine that may be important in terms of the leaf management system. We certainly need to identify the states, the transitions and the state machine diagram, which we will start with by having a protocol state machine diagram. So, what we identify is we have seen that a leaf is first created through a request, and then it goes through an approval process, and it may be approved, it may be regretted. If it is approved, then it may be averled or it may be cancelled. If it is averled, then it will be deducted and so on. So, we can model this whole information in terms of a life cycle of the leaf. You can say that the leaf has a life cycle which has these different kind of states. So, we are first just trying to, in terms of building the protocol state machine, we are just first trying to identify what the different states could be. So, when the leaf is just first created, you would recall that while a leaf request is put in, the leaf has to validate itself and make sure that the leaf being requested is a valid leaf. So, when that happens, it is just a new leaf, and after the validation, when the request has been when the request has been registered in the system, not approved yet, when it has been registered in the system as a valid leaf, then it could be in the requested state, and based on the request, the lead or the manager may or may not approve, and therefore, it could go to the approved state or the regretted state and so on. So, if we just follow that, then we will be able to identify that different transitions for the leaf life cycle, like in terms of new to requested, requested to approved, approved to regretted and so on. So, basically once you have identified the states, you look at what are the transitions that are possible and what are the triggers and preconditions for that, if that can be defined, and you try to do that. So, this is where I present the leaf system in terms of the state machine. This is the initial state, and certainly this is the state where the leaf has been created. So, you have a new, and then based on this you have a request. So, what is this transition? In this transition will be possible if the new leaf is a valid one, right. If this is not valid, then it is not possible. So, if I write in that notation, then this has to be a valid leaf and the trigger is a request. What is a post condition? The post condition is block dates. Why? Because if somebody has requested for a leaf, say from 1st June to 3rd June 2016, then once the request is registered, that is what we are designating by moving the leave to the protocol state requested, then those dates must be blocked, so that no further leave request or other request can be made on those dates. So, we can clearly see that as this transition happened from new to requested, this is the precondition that we need, the trigger is the request, and this is a post condition that must happen. So, in a similar manner we could continue on that. If a leave has been requested, then it may be approved. You could decide further. This is just I have put just a cursory transition information. You could put more transition information. You could have multiple more states here depending on the different situations of approval. Some approvals are conditional depending on the validity or availability of the supporting documents. Some are direct approvals and so on. So, you could decide to have more protocol states describing that, and then have more preconditions and post conditions defining that, or otherwise a requested leave could be regretted. So, any of these will have a post condition of notification, whether it is approved or regretted, there will be a notification that will be done, and the leave will be in one of these states. An approved leave may be cancelled, could go here. It may be revoked. Actually, we could have this is regretted. It should not actually happen here. A better way to model could be I can have a revoked state, protocol state. So, I can a manager could revoke an approved leave, and a revoked leave cannot be availed any further. An approved leave can be availed, and then any of these, if it is an archived leave, it is a request regretted leave, a revoked leave, or an availed leave could actually go into some kind of a we can say I mean, for the search of a word, a dead leave, as to where no further changes can happen to that leave record, which is then archived in the system. So, this is just an outline showing you what are the different transitions that can happen. If you analyze further, you will. So, this just gives you the protocol state diagram. So, in each one of them, for example, in the requested, you could now make this protocol state into a behavioral state by defining the exact entry, exit, and the do activity here, because in the requested state, before the transition happens, you have the activity where the manager or the reporting manager of the requesting employee has to look at this leave, consider all factors including the documentation and other conditions, and then take a decision on that. So, those could be the activities in each one of these states that we identify and start encoding, putting into the state machine diagram. More and more we do that, this will slowly become a more complete behavioral state machine diagram for the leave management system. So, this is just to show you that even such a simple system as for leave management has a lot of scope. It does not immediately look like a problem. I mean, it is not an electronic problem or a physical problem like the temperature controller or the calculator, where the states look to be more obvious, but here you can see that the dynamics of the system do again depend on a set of states, which is very typical for any of the complex systems that we would like to model in UML, and state machine diagram for that purpose or state charts for that purpose turn out to be really useful tools in our modeling dimension. So, to summarize, continuing on the discussion on the state machine diagram, we have in this module discussed about protocol state machine diagrams. We have talked about protocol states and protocol transitions along with the precondition and post condition, and we have taken a look into how LMS, the state machine diagram for LMS can be constructed.